record. Okay, normally it says that it's recording. I didn't hear that, but it says it's recording.
I heard it.
Oh, so super duper duper. All right, so let me introduce you again. So we're really delighted to have Miles back for the second of two talks. For those of you joining for the first time, which you shouldn't be because the first talk was excellent, and I'm sure the second talk will also be excellent. Miles is at the Flatiron Institute from 2017 as a research scientist in the Center for Computational Quantum Physics, earned his BS in physics and math. Oh, you got the dual degree, very nice, from Georgia Tech, and a PhD from UC Santa Barbara with postdocs at UC Irvine and Perimeter Institute, and is the lead developer of the iTensor software, which he has been thoroughly encouraging us and everybody else to use. So with that, we're really glad to have you again, and please take it away.
Okay, thanks so much, Will, and thank you all for being here. And those of you who came on Tuesday as well, or if you need, the video is online, so you can check that out. I'll do a little bit of a review of Tuesday's material too, just a very, very short one. So I'll be talking about tensor networks and quantum computation, like the connections between those and the kind of interactions that are going on right now between those two topics. So Tuesday we covered what those are, tensor networks and tensors, and the idea, one key takeaway from Tuesday was the idea that anytime you see a quantum circuit, which is a program for a quantum computer in some sense, it's also literally a tensor network in every instance. You could always just take every single gate, every single element, and just map it one-to-one to a tensor network. And if you could contract that network of tensors meaning just, they're connected by saying this index contracts with this one, If you could contract it, you could find the whole quantum state that the circuit prepares, but that could be very exponentially costly. So you need extra tools to do that well. And I talked about some ways to simulate quantum circuits using those more advanced tools that I'll review in a second. So today's talk, I'll go into some more applications of this toolbox. And specifically, I'm going to try to land on 2 points, and hopefully you'll have time to do that in an hour. And one of them will be that in one case, we were kind of shocked to discover that we could take a seminal quantum computing algorithm, the quantum Fourier transform, as part of Shor's algorithm, but other algorithms too. We could take it and actually pull it back all the way from the quantum world completely into the classical world. So it's actually, in some sense, really just a very good classical algorithm, but written as a quantum circuit. We'll talk about the caveats, though, of that. You can't use it on every function, but on quite a large set. And then the other one is this simulation that our group did recently of a certain spin model undergoing dynamics on a certain heavy hex lattice that was put forward as evidence of quantum utility. And I'll talk about that whole story briefly. Okay, so reviewing tensor networks. The idea is that more and more these had been thought of as tools for working with wave functions in the past, but I think more and more now they're being understood as ways to compute in high dimensional spaces. So just basically think exponentially large vectors and matrices, but then broken down as a network of tensors. So why do we need tensors? One very common setting that we'll see, for this talk will be that anytime you have a many body quantum wave function, and here by many body, you could think many qubit. So I'm labeling the qubits by S1 through Sn here, and they take the value 0 or 1 because it's like quantum computing, thinking of bits. Then if you just write down the most general possible wave function for what a quantum computer could be doing, then naturally the amplitudes, which have all the information, have the same number of indices as the bits. And so it's a big tensor with n bits. Here I'm just drawing 6 so I can fit it on the slide. So that's the wave function in some sense. That's all the information is packed into this huge tensor. But actually imagining if someone even could compute it for you, but then giving it to you, you couldn't even really receive that gift. Like if someone said, here's the wave function, you wouldn't be able to even hold it in your computer in general, because if you just count the number of entries or components inside of it, it's a very simple, argument to show that you'd have to store 2 to the n numbers. Here 2, if I'm thinking of each index of being of size 2. So it's an exponential scaling of memory. And for the same reason, if you try to compute anything, like even if you try to compute a local observable or some expectation value, that would also scale exponentially in n. So mathematicians call this the curse of dimensionality, and it's a well-recognized problem of working with higher order tensors, meaning tensors with more than 3 or 4 indices, is this sort of blow up of cost. But there's a nice way out of this problem. There's a few ways, but this is maybe the nicest way, which is to break the tensor up into a contracted network of other tensors. And the idea is that now the tensors in this network should all be kind of small, like low order, like maybe order or anything from order 2 up to order 4, or maybe order 5, but not more than that, basically. And then you make a network where each of these lower order tensors in the network carries 1 or maybe 2 of the original outer indices of the original tensor. So it's like a model of the tensor. You can kind of think of the tensor as having like a skeleton or like some internal structure that's being revealed. And then there's principal ways to reveal it, or you can think of turning the arrow the other way and saying, let's just hypothesize that this tensor really is this network, and we'll just guess it's this network all along, and then our job will be to figure out what numbers need to go into these smaller tensors, or initialize them in some way and then operate on them, and then that's virtually like operating on the big tensor, that kind of thing. Then that's sort of some general picture. The actual kind of workhorse of most tensor network methods, although later I'll bring up a more two-dimensional one, but this is sort of the original and best one in some sense in a lot of ways, is this one-dimensional network called the matrix product state. In the math literature, it's called the tensor train, which is probably a better name. And the idea of it is you factorize the tensor into a chain, and you might wonder, how do I know what order to put them in the chain? And often it's kind of domain specific, but there usually can be a sensible order in many cases. And the idea is that your main control parameter, your main thing that controls your costs and also your expressivity and kind of the thing that captures the complexity of the tensor, is called the internal rank, is the math name, or physicists call the bond dimension, because it's the dimension of these bond indices going through, and that's often notated as chi. And the idea is that if chi can be held constant, or if you're working at a constant chi at some point in the algorithm, then the cost of doing things is linear in the number of sites, or qubits in this case, which is pretty shocking. I mean, I should have put a slide on this, but that means if you can capture the state of a quantum computer in this way, then operations on this classical model have the same scaling as an actual quantum computer. So you go to a quantum computer and you say, I want to act a gate somewhere, and that is something that is kind of constant in the number of qubits, basically. Here it's linear in the number of qubits, which is not that bad. I mean, it's very close. Maybe you could even argue that it's also linear for the actual quantum computer, because you have to sort of operate some machine that kind of indexes to that gate or something. So basically all I'm saying is that the costs are very, very closely analogous to a quantum computer, an actual quantum computer, if this chi remains modest in size. And that depends on the application, whether it does or not. In fact, what determines chi, or what is chi really tied to, this bond dimension or this rank, it's really tied to the amount of quantum entanglement in the state that you're representing, because it bounds it. So if for any given chi, the quantum entanglement of the state across that division into the left and right, you can easily prove can only be at most log chi. So if the entanglement pushes up and up and up, chi has to grow as well. So these are tied together. And in many cases, entanglement can grow exponentially. So chi can grow linearly, and that can be expensive if that's happening. So the idea is that these tensor networks, these matrix product states on this slide, but more generally, all the other tensor networks are analogous. They're very, very good at capturing low entangled and moderately entangled states. But if you ever encounter some kind of application where the entanglement needs to grow very fast or to high values, then, like, for example, a totally random state picked from the entire Hilbert space, something like that, or acting with a random quantum circuit for enough depth onto a quantum computer, things like that, then these would fail. But then the interesting thing is that a lot of applications envisioned for quantum computers, sometimes it's just assumed maybe, or not even really questioned about whether the entanglement gets high or not. And so some activity that us, but also other people have been involved in the last few years is actually kind of going one by one to different applications of quantum computers and checking this. And of course, in some cases, it's very high. I'll show you one in a little bit. But then in other cases, it's not that high. And this was something that needed to be looked into. Now, kind of, still on the topic of tensor networks, by request on Tuesday, I mentioned different applications of them in physics and otherwise. And I mentioned lattice gauge theories. I'm not at all an expert on this topic, but since there was a request on Tuesday, I thought I would just put in one slide, basically to give a reference to a paper that looked nice to me about this topic that's very, very recent, just last month. And it's just to say that tensor networks are finding, wider and wider applications even in physics. So there's been, you can kind of look, there's a very nice list of references at the beginning of this paper, and you can look back and see that there's been many previous studies of lower dimensional gauge theories, lattice gauge theories, or abelian lattice gauge theories. And then this paper is trying to push into 2+1D lattice gauge theories with non-abelian, I don't even know the word, but it's a non-abelian lattice gauge theory. So just showing that this is a field that's being pursued, and it seems like a really nice direction. And the key point is that these tensor network methods don't suffer from the sign problem that's like a famous issue with Monte Carlo methods that are applied to these same kind of systems. So there's no sign problem, and instead you have what you could call kind of like an entanglement problem, which is that these internal bonds might need to grow to be big, but you could kind of argue that the entanglement problem is a much better problem to have in many cases than the sign problem. It doesn't scale as badly, basically. Something else very different, another person who came to the talk on Tuesday asked about tensors living in spaces that aren't tensor products, or aren't, or have sort of these sectors that are indexed in ways that aren't tensor products. And this is actually a really fascinating topic that I've been learning even more about recently. But it's been known in various guises in physics for a while, related to like anyons and topological order and these kind of concepts. So again, I just wanted to put a few recent references. There's many more actually in the last, especially 5 years, or maybe 10 years. But this is just to say that tensor networks are actually pushing into pure mathematics in some sense now. So with these developments that have happened for understanding things like anyons in 2D systems, that's more of a picture of that on the right, that people have been realizing that actually you can answer a lot of questions about what are concrete representations of things like quantum groups, Hopf algebras, this kind of thing. And it turns out that you can understand all of this language very, very concretely in terms of tensor networks. And if you look in the math literature, you'll see that there'll be pictures like this, and they'll say this is some kind of description of objects living in a category with morphisms between them. It's sort of very abstract. But in this language, it's extremely concrete. Like this thing is just a bag full of numbers that has 3 indices, and there's just very specific numbers you put in here. And then you do a sum, it's just adding and multiplying. You just multiply these numbers with this other bag of numbers over here. And then you show that there's some matrix that rotates you from this contraction of 2 tensors to this contraction of 2 tensors. And you can print all the numbers out and look at them on your computer. And it's sort of it's really just like linear algebra in this language. So I like it because it sort of brings some of these very abstract topics totally down to earth, in fact, because you can really just do everything on the computer. Okay, so then example application number 3 of tensor networks. So that was just kind of to show how broadly these are being applied these days. There's many other things too, chemistry, machine learning, other fields too. I wish I had time to go into. But the example application that'll be relevant for today, in kind of to finish this introductory part, is quantum computing. And the thing I talked about at more length on Tuesday was that when you take this MPS tensor network form of a tensor, you can use it as a tool to run quantum circuits. So you can view the qubits at the beginning as already being in a matrix product state form, because you can kind of see this 1D structure, and that you can imagine fake bonds connecting them going down, but they're all of size 1. Then you can just start pushing the MPS through the circuit and sweeping it through. And there's simple algorithms that you can do to absorb the gates into the MPS. And as you do, the internal bonds grow generically. Or they could grow if the entanglement is increased by the circuit. It depends on the circuit. And you keep pushing them in. And as you do, you absorb all the gates. And when you're done, if everything goes well and this bonds don't grow too big and you can store them on the computer, then you actually have the entire wave function on your computer afterward that the quantum circuit prepares. And then you can study it, sample from it, compute correlation functions, all kind of things very efficiently using nice MPS algorithms. So one application of this that I was involved in that was a lot of fun was that in 2019, Google famously put out a paper where they did a really actually very impressive experiment running a certain kind of random quantum circuit. Random in the sense of all the single qubit gates were chosen randomly from a set of 3 different gates. And then there was a sort of fixed pattern of 2 qubit gates that keep pushing the entanglement up and up and up. So they ran this circuit and then sampled bit strings from it, and it prepared a very random kind of state. but it was a very specific random state because it was the state prepared by this specific circuit. So even though you do it randomly, once you draw the circuit, you kind of freeze the gates. You say, these are the gates we're going to now use. And then you run the circuit over and over and over and sample a lot of bit strings. And so you're sampling from some kind of very arbitrary distribution, but which is hard to sample from for a classical computer, even though it has no real practical meaning or anything, but it is mathematically well defined. So that's what they did. They ran this circuit, and a key point though is that they didn't actually get the exact quantum state prepared by the circuit. They just got some small fraction of it, and they were honest about this in the paper, and they reported what fraction they got. I think it was like 0.02% of this enormous state. And so we did two papers, kind of trying to investigate this and say, okay, how hard was this really? Because Google had claimed that doing the same thing on a classical computer with the best known methods would take 10,000 years. So that really grabbed people's attention. And so in the first paper that we did, we didn't succeed in doing the same task, but we did get kind of close. But one thing we did along the way is that we first tackled one-dimensional quantum circuits. Google did a 2D quantum circuit. We said, what if we did 1D random quantum circuits? And it turned out, using these matrix product state methods, you can show that you can basically get any, you can simulate any one-dimensional quantum circuit at all, like really any, up to a certain fidelity that's 99.99%, basically generically. And that might still not be high enough for some applications. I'm not saying that P equals NP or anything, because you could encode some kind of, certain discrete math problems in 1D. But for these kind of near-term applications that people are envisioning, this is already a fidelity that's comparable to some of the best hardware today for 1D circuits. Then we pushed to 2D circuits using the methods in this first paper, and we got pretty far, but it wasn't as far enough. We didn't get the same fraction that Google did. But later, with some more other co-authors, we basically tied Google's 2019 result using some more advanced techniques in a paper that came out in publication this year. So in the meantime, another group, though, in Beijing really handily beat Google's result using a GPU supercomputer. So it's interesting to see that kind of back and forth that's going on between the classical world and the quantum experiments. Okay, so that was kind of some background. Other activities that are going on in tensor network applications, and this kind of back and forth with quantum computing. So let me now talk about some more recent. We were kind of motivated by this story to keep going and investigating other aspects of quantum computing through the lens of tensor networks. So this was fun, but the problem of it was that these circuits were very kind of academic. Like, they were just these random quantum circuits, and we were just sort of trying to assess the capabilities of tensor networks in some kind of general random task. So then the question is, we have this tool to run quantum circuits, and we could, say, do almost all 1D quantum circuits up to this very high fidelity, and push, with a lot of effort, we can push on certain 2D quantum circuits. What if we now turn back to the kind of like stable of quantum algorithms, these different famous quantum algorithms like Shor's algorithm, Grover's algorithm, other things people are proposing? What could we do? Like, what's the real power of these classical simulation methods, and can we learn something? So just last year, with this really great undergraduate student, Jilin Chris Chen at UC Irvine, who's at Irvine at the time and now at Caltech, and with Steve White, who actually was the inventor of these matrix product state methods originally, we investigated Shor's algorithm. And I'll kind of break that down for you. And just jumping to the punchline, we did not simulate Shor's algorithm. Otherwise, that would be kind of a big deal in the information security community. So we didn't crack any codes or anything. But what we were interested in is it really hard to simulate? We figured it was, but why? Which it has two halves, and which half makes it hard to simulate? Are both halves hard, or just one? And what's the story? And we found something very interesting. So let's see how I'm doing on time. So by way of kind of introduction, Shor's algorithm is in some sense probably the most impressive quantum algorithm still. Because it solves a very hard problem with a relatively shallow circuit. And it's very ingenious how it works. And it's a quantum algorithm for factoring large numbers. So you input some large number, say that you know or suspect is the product of two primes, and it will, alongside with some side calculations you do classically, it will help you to factor and discover those two primes, say, that made up this big number that you picked. And technically, Shor's circuit, the quantum part, doesn't do the factoring directly for you. You have to kind of help it out a little bit. You have to provide some kind of input number and do a little bit of classical post-processing at the end. But all those are kind of cheap and you can do polynomially. It does this hard part that is called the order finding problem. So you have this big number m you want to factor. You choose a second number a at random, and a just has to satisfy some very easy checkable properties. Like not all numbers will work, but you just pick a few at random and kind of filter out a few, and you can easily find one that satisfies certain properties. Like it has to have a certain greatest common divisor with m or something. Then once you've picked such an a, which you can easily do, you plug it into this circuit finally. And the circuit runs, and what it does with high probability is it computes a number r for you. And this number r has the property that if you take a to the power of r mod m, you get 1. So you can think of running like a random number generator where you take r to be 1, 2, 3, 4, 5, and you keep increasing r, and a to that number mod m is all kinds of different numbers. I'll show you an animation in a second. And eventually when you get to a certain value, you go all the way back to 1, which is kind of like if you had taken r to be 0. So it's the idea is this a period of this random number generator that you're running, and Shor's will figure out that period for you. Once you know r, you can then factor m efficiently. There's a straightforward way. So how does this work on the quantum computer? What you do is you first prepare 2 registers of qubits. So these are just 2 collections of qubits that you prepare at the beginning. The upper register, the lower register. The job of the upper register is basically just to be in a superposition of all possible numbers. And the lower register is like a memory where you're kind of holding your calculation and as you go through. You prepare the lower register to be in the binary representation of the number 1. So here's, all zeros, and then the last bit is 1. And then you prepare the upper register in a massive superposition of all possible numbers, integers that it can be in. And you do that very easily by just acting with a Hadamard gate on all the 0 qubits. And so this is a massive superposition, but it's totally unentangled. And it's very easy to prepare classically or in a quantum device. So that's a well-known kind of starting point for lots of quantum algorithms. Then I'm not going to go into the details of this part, but there are these papers you can look up, and they provide quantum circuits that go into these boxes. And they're kind of complicated, but otherwise pretty straightforward. They're just doing things that are like additions and multiplications and mod operations and things like that. Just using kind of analogs of classical logic, but written out as gates. And the idea, though, is that they're controlled by each of the qubits in the upper register. So the first gate, what it does is it takes this bottom register, which is in the number 1, and it multiplies it by a to the 1, basically 2 to the 0, but controlled by x0. So if x0 is off, if it's 0, you don't act with this gate. But if it's on 1, you do act with this gate, which multiplies by this number mod m. So there's a mod at the end of this gate. And then you have the next qubit up here, x1. If it's on, you multiply the bottom register also by a squared, which adds here in the exponent, controlled by x1 mod m. And you keep going like this. And the idea is when you're done, if you think of the upper register as representing a number x, but it's in a superposition of all possible x's, the bottom register is being put into the state a to the x mod m. So it's in this massive superposition of all kinds of different outputs of this function a to the x mod m on the bottom. So let's kind of see what that actually looks like. So here I actually worked a concrete example out where if you have m equals 35, a equals 12, that's like one of the number you pick at random. Then it turns out, coincidentally, that r also happens to equal 12 in this example. It doesn't have to equal a in general. And then we can just visualize what the lower register state is. So if we unroll the lower register state as a long vector, and you can imagine this vector keeping going off to the right, but I only will need this much room. Then we can just, as the circuit runs from left to right, we can visualize what the state looks like. And basically, it just looks like this. The circuit runs and runs and runs, and this process just gets generated, and it's like putting delta functions in certain places in the state. And what I want you to see is that they're basically going in kind of pseudo-random locations. That's kind of the point of this slide. And if you count, turns out to be 12 of them. And that's the idea that that's the value of r, it turns out. So the point is that this state has sort of very little structure. It has the structure of like a classical random number generator, but that's like very little structure, practically speaking, in terms of something you could try to compress. So it's very incompressible, meaning that a tensor network won't do a very good job at all of representing it. And it turns out to have high entanglement. So that's sort of an insight into like why you shouldn't worry about classical simulations, simulating shores and breaking any cryptography anytime soon. And it turns out the bond dimension, if you represent this as a matrix product state, is actually exactly chi equals r. This is something that's actually been known for a long time in a different language. And R is typically very large if M is large. But interestingly, if you could simulate this part, you actually wouldn't even need the second part that I'll show in a minute. You could just look at the MPS representation of the state and look at its bond dimension, its rank, and it would just be R, and you could read R off directly, and you wouldn't need the rest of the algorithm. So that's just kind of a neat point that we learned as we were going through this. So much for that part, but that's just all to say that, you can't really do that part classically as far as we know in general. There is a neat paper though, by an author, I think it's Graham Smith, saying though that like, he pointed out something related to this a number of years ago, saying that it's not that simulating shores is generically hard. If you could somehow cherry pick problems where R is small, you could do it. It's just that, general cryptography, they would pick a problem where R isn't small. So it's not like a general solution for all factoring. Okay. Any questions about that part? Okay, great. So then I'll go on to the second half of Shor's algorithm. So the first half is doing some kind of, in a way it's doing kind of classical logic, but it's doing it in a superposition. So then the second half is saying, great, we prepared the superposition, but we can't really practically pull that information out of a quantum computer. It's this massive superposition, but if you do a measurement, you will collapse the state and only see one of these peaks. So you won't be able to really count how many peaks there are very efficiently. There could be a very large number of them. So what you do next, and this was kind of the really ingenious part of Shor's algorithm, is that you perform a discrete Fourier transform on the upper register. And this is done through a circuit that was known at the time called the quantum Fourier transform. Technically, you use the inverse one, but it's very similar in concept, and the circuit is just the reverse. And so now that's where we focused on this project, was we said, okay, we've kind of understood some things about the first part. What about this second part, this quantum Fourier transform? And the idea is because of the mod going on in the lower register, it sets up a periodic structure with this period of R. And then by doing a Fourier transform and then looking at the peaks of the state that come out, which you can get by sampling the state at the end, by collapsing the state, you can then detect R. So that's the idea of the rest of the algorithm. So we wanted to look into the quantum Fourier transform. So the quantum Fourier transform, again, as I said, it performs a discrete Fourier transform. So if you took some generic wave function as input, and you just unrolled it as a large vector, just treating the qubits as binary numbers that count from 0 up to 2 to the n minus 1, and just ordered the amplitudes kind of left to right as a huge vector, and called that vector fj, then what this circuit does is it does this sum, sum of fj with these phase factors that are kind of well known from Fourier transform theory to give you these other values fk. So you can think of it as outputting a new quantum state, which is another big vector, but now the values of that big vector are the discrete Fourier transform of this input vector fj. That's just what it does. There's some well-known circuit for it. I'm not going to have time to unpack the details of the circuit, but the bottom line is it's made of just really two things. There's Hadamard gates, which are kind of a well-known quantum gate. And then there are these things called controlled phase rotations that say, if x2 is in the one state, then rotate the one state of x1 by a certain prescribed phase, otherwise do nothing. And then there's a bunch of these kind of spanning different distances with different phases that have a very simple formula you can write down. And those are the only two kind of gates in the circuit. So it's just a bunch of those rotations and Hadamards over and over and over. It's a very nice circuit, actually. But as I mentioned on Tuesday, all quantum circuits can be directly interpreted as a tensor network. And so one thing that the student Chris did on this project was figure out that you could combine all of these controlled phase rotations into a single tensor network going down. So that's this chain that kind of does like a multi-phase rotation on all the other qubits that aren't represented by this black dot. So the dot's the control. And if it's one, then you do a multi-phase rotation in parallel on all the other qubit lines. And then you go down and down and down like that. And then there are these Hadamard gates putting everything into a superposition as you go through. But this is just a tensor network. So these are all simple tensors you can write down that are just a 2 by 2 by 2 by 2 array of numbers or a matrix here. You can write all these down and kind of fill out this network very easily. And then most importantly, and this is what he tried, was you can now think of each column as a kind of generalized matrix product state. I didn't have a slide on this, but it's called an MPO. And it's like the operator analog of a matrix product state. And I'll show you what that looks like. So we think of this first chain as already being a kind of tensor network operator. And the second column as well. We multiply them together. And then we just keep multiplying them across. And this is something that we can do in like a one line of code in our tensor network library, iTensor, that we used. And when we're done, we have this tensor network representation of the whole circuit. I mean, this always is true formally. But what was kind of shocking to us is that when he tried this out, the internal ranks or bond dimension was just 8, only 8. And that was true in a general sense. This circuit would be the same circuit acting on any input you want. And formally, it's much more than 8. But what I mean is that when you're working to double precision accuracy, so we would do these kind of roundings that you would do when you do singular value decompositions, where if you see a bunch of small singular values below a certain threshold, you can throw them away. So he was doing that, and there was a bunch of them, but they're extremely small. So when you throw those away and kind of keep things to double precision, this internal rank or bond dimension is 8. And so you can think of this object as this matrix product state that I drew earlier, but just with 2 lines coming out of every tensor instead of 1. And that's this thing we call an MPO. So it's kind of like if an MPS is analogous to a vector, an MPO is kind of analogous to a matrix, but it's an exponentially big matrix. However, it's one we can store easily on a computer because we just store all these tensors. And what was neat too is that this result holds for any number of qubits. And Chris is a really strong mathematician, and he actually proved that in our paper that's online. So he actually proved this a bound on the ranks, and then showed that this bound holds to any number of qubits, and even gave a really nice argument. And he gave a colloquium talk on this at the Simon Center for Computing in Berkeley earlier this year that I would highly recommend. It's a really excellent colloquium that he gave. So please check that out. So already this says something kind of profound about the QFT. It says we can always operate the QFT on a classical computer for any input whatsoever, as long as we can represent that input also on a classical computer. So, the title of the paper was actually "The QFT has small entanglement." So what's an application of this, though, that you can actually use? And this one I think is pretty fun, is that we could use it to Fourier transform functions, right? So we're taking this algorithm that was really kind of envisioned for running on quantum hardware when you were doing things like Shor's algorithm. And we could try it today as a tool to just do applied math applications. And how does this go? It works by first you encode your function that you want to Fourier transform as a quantum state. And this is just a formal step. And here you don't do any work, but you just sort of think this way. You say, let there be a quantum state where all the amplitudes are the values I would get by plugging in all the integers into my function, stepping from 0 up to 2 to the n minus 1. And then if you want, you can treat those integers as indexing over a continuum by just taking a very fine grid spacing. So you could think of integers here divided by that grid spacing, and you can fill out a continuum very, very finely indexed by these qubits. That's a very common idea called amplitude encoding, and it's used all the time in the quantum computing literature and other literatures. But then the really non-trivial part is that for many functions, you can then compress that quantum state into a tensor network. And there's many different ways to do this, and just some very, very nice ones I won't have time, unfortunately, to unpack. But there are very nice, very efficient polynomial time algorithms given a function f to load it into an MPS like that. So that part works extremely well. And then we have this QFT tensor network operator, or MPO, that Chris computed. And this is something that you can compute just one time. You just have it on your computer already once and for all. It's something I can email to you if you want. It's just already computed and saved. And you just apply it onto your function in this tensor network language. One interesting detail is that here, these qubits represent different scales of the function. So instead of kind of representing space, where this would be one point in space, another, and you're kind of going left to right, here, left to right means something like coarse features of the function, finer features, finer. So you don't actually need very long states. Like once you have, say, 20 indices, you have a resolution of 1/2 to the 20 in terms of your grid point spacing. It's extremely fine discretization of the continuum. And actually, many functions compress extremely well. There's actually a really nice mathematics literature about this, in fact, with proofs about classes of functions, and a very deep understanding, in fact, now of which functions compress. But here's just some examples of this. So if you take a single cosine, that's one of the easiest cases. It compresses provably to a rank of just 2, bond dimension 2. If you sum 20 cosines, that compresses to a bond dimension of 18. Very, very modest, because in quantum many-body kind of condensed matter applications, we routinely work with bond dimensions more like 1,000 very often. So 18 is like just a second running on the computer. And you can even have very sharp features in the function. So this is the kind of the non-trivial part. You can have step discontinuities, you can have cusps, sharp features, and resolve these on these grids of spacing of 1 over 2 to the 20, 2 to the 30, very, very well. And the bond dimension is just like 9 in this case. So it's extremely good compression of these functions. And you can do 2D and 3D functions as well, very straightforwardly. And then we knew you could use the quantum Fourier transform to Fourier transform these kind of functions. But then the question is it fast? Does it buy you anything? So the natural baseline we'd want to compare to is the famous fast Fourier transform. And now the fast Fourier transform doesn't take advantage of any structure in the function. It doesn't care if there's cusps or if it's smooth. It doesn't know anything about compression or matrix product states. There, you just have to unroll it as a big vector. So it just has a certain scaling having to do with how many grid points you have once and for all. And it just scales the way it does and costs what it costs. So there's its timing, and it's very, very fast. But then if the number of grid points is going up exponentially, then you have to do exponential work. So it goes up like that. And then what's interesting is when we do the quantum Fourier transform on these functions, here it's now function dependent. If the function compresses well, everything goes well. And I'll show you in a second, if the function doesn't compress, things aren't so good. But remarkably, when we tried these functions that compressed well, the quantum Fourier transform at first was slower than the FFT. It was no surprise because FFT is extremely optimized algorithm. But then for enough grid points, there's actually a crossover. And so we could actually see that on fine enough grids in 1D, the quantum Fourier transform actually beats the fast Fourier transform. So then that was something that really was neat to see, because here's one of the best known, most optimized algorithms in applied math. And then here we're able to beat it by taking something envisioned for quantum computers, bringing it back into classical computers and running everything classically. So that was really exciting. But then, as I mentioned, it depends on the function. So if you actually take a completely random function, by which I mean just put totally random values on every grid point, and there's no relationship from one grid point to the next, that can't be compressed. And so you can't get this advantage of the QFT, and things are much slower than the FFT. So it's not saying it's some universally faster thing, but it is very general purpose. You can compress a very wide class of functions and take advantage of this. Okay, so that was kind of the end of that part. And to summarize that part, that was just kind of the story of what we've learned so far by looking into Shor's algorithm from a tensor network point of view. And we believe it's most likely hard to simulate overall. But surprisingly, the second part, the QFT, is not only, somewhat easy to simulate. It turns out it's extremely easy to simulate. And in fact, we can just put it into a tensor network, the very small size, and save it and use it as a classical algorithm. And it can beat the fast Fourier transform. So that was a really kind of fun project to do. I'll pause if there's any questions about that part.
Just as a sort of thinking about how, if one were to want to compute Shor's algorithm, you'd still need a bona fide quantum computer for the first part, and then this takes the place of the QFT that you needed to turn it into something useful. Okay, but on its own, this can be used as an alternative for the fast Fourier, or just Fourier. Okay, but yeah, in order to beat Shor's algorithm, you do still need that first part, which is classically practically impossible. Okay.
Yeah, great. That's a good summary. Right, because one of the questions we got the most after we wrote this paper last year was, should we be calling the NSA? Did you guys just solve factoring? And because the QFT is so closely associated with Shor's that people immediately think of Shor's. Even though when we wrote the paper, we barely talked about Shor's in the end. But people asked us, have you solved Shor's? Have you solved Shor's? And in a way, that's kind of, this plot summarizes the situation, because Shor's would put you up on this black curve here. And so by the time you got to the QFT, you would have like a kind of pseudo-random function, because it's some cryptography function. And so you'd have this pseudo-random function, and you wouldn't get any benefit classically by trying to work with that. So that's a good summary. But then, interestingly, we can now kind of detach the QFT from Shor's and say the QFT is useful on its own, in fact, as a classical algorithm. And so that was really neat. And I really like that for a lot of reasons. I mean, another reason is that it's like literally, if nothing else ever came out of quantum computing, if tomorrow all the quantum computers never improved even one bit more, and nobody ever thought of another quantum algorithm. And of course, this isn't going to happen. They're improving a lot, the quantum computers. But even if that never happened, already that field has already generated a very nice classical algorithm that could be used all over the place, and we need to be using more and more. So I just mean, I expect this continue to happen, where there might be all kinds of nice developments in quantum computing that are kind of streaming back into classical computing. I mean, at least I hope that continues, and vice versa. Ideas are also crossing from classical computing into quantum computing. Like, for example, there's a group, especially this group at Quantinuum in Colorado, which has one of the best quantum computers in the world right now. They're also very actively pursuing algorithms based on classical tensor networks. So they take tensor networks, they're inspired by that classical work, and they're building their quantum algorithms around tensor networks quite a lot. So there's a lot of ideas flowing back and forth now between these two areas. So kind of speaking of which, then the last topic of today, and thanks for bearing with me packing in multiple topics in the talk, but I think we'll still be on time, is this topic that Will was asking about, which is this recent story about Ising dynamics on a heavy hexagon lattice. And so this was this paper that came out, and then our group was able to simulate the same results basically within 2 weeks. And this is around the question of, have quantum computers demonstrated utility? And I'll say, first of all, I really like that question a lot, because I mentioned earlier this topic of supremacy very briefly that Google had put forward. And utility is really what we want to see, right? We want to see that quantum computers not only are just sort of powerful in some kind of raw sense, but are actually delivering value, right? Everybody wants to see that. So I really kind of celebrate that question, and I'm glad this paper is pursuing that. But of course, there's an important activity of classical world checking these claims and sort of making sure that the problem is hard enough. So this was done with a different group of people. Most of all, Joey Tyndall, who's a postdoc currently here at Flatiron at CCQ, which is our quantum center at Flatiron. And also very much Matt Fishman, who really envisioned a lot of the code and algorithms and worked closely with Joey on developing all the methods. And then Dries Sells, who is an expert on quantum computing and really kind of helped guide this project and encourage us to go after this. And then there's 2 papers on the archive, a really nice methods paper also by Joey and Matt about more details of how the algorithm works, which I'll kind of have to be very brief about today. So this June, just this summer, 2 months ago, there was all of a sudden a paper just sort of appeared in Nature. It didn't even go through the archive, with a lot of press coverage kind of immediately the same week, covering a new quantum experiment that came out of a group at IBM. And this, although the paper is worded very carefully, the media coverage, including the cover of Nature, was sort of said some very strong things, I would say. So the paper was very careful, and it said, evidence for utility. But already on the cover of Nature, you saw a phrase, physics that classical methods can't reach, right? And then you see articles saying that this IBM beat a supercomputer, which already, raised some red flags for us, because I wouldn't, as I said earlier before the recording started, I don't even quite know what that means to beat a supercomputer, because it's not that supercomputers have some kind of inherent speed. I mean, they kind of do if you just ask them to just add up a list of numbers or something. But in terms of actually solving a problem, the speed of a supercomputer depends on what algorithm you use, right? So there is no such thing in my point of view as beating a supercomputer. It's just like, what are you doing on the supercomputer? So already, we were kind of wondering what's the claim here, But clearly they were doing something that could be very hard, which is simulating quantum dynamics. That's known in general to be very, very hard to do classically. And we're still working in the classical world on methods to do that better and better. There's been improvements, but it's one of the tougher problems for our field. So what did the experiment compute? It computed quantum dynamics. So you take a bunch of sites that you think of as spins. So the qubits, you view them as quantum spins. So they can be up or down, which is kind of a classical state, but they can also point, left or right, which is like a quantum superposition of up and down. And then you make them go through these kind of stroboscopic, what's called flow-K dynamics, which is really just a fancy word for saying stroboscopic, like the Hamiltonian acts in these kind of discrete large steps. And the dynamics is just that of the transverse field Ising model. So you have these kind of ZZ coupling, this kind of classical, but you also have this field that points in the X direction that makes quantum superpositions of states. And then you time evolve over and over and over with this same time evolution operator U. I don't have time to kind of go through all the background on that, but basically just imagine these spins rotating, flipping, entangling with each other, getting more and more complicated in time. And time here is just applications of layers of this U operator onto all these sites over and over and over and over. So it is a very worthwhile problem because these kinds of dynamics have all sorts of applications back into fundamental questions in condensed matter about heating, about dynamical phase transitions. So it's a very great use of quantum computers, and we'll see in the end the experiment was very accurate, and so it's a nice experiment. One of the nicest things about the experiment, in my opinion, was this zero noise extrapolations that they advertised a lot in the paper. And the idea is that we're still in the era where this hardware has a lot of noise and a lot of difficulties to control. So they had a great idea, which is to say, rather than trying to turn the noise down, let's turn the noise up, because that's easy to do. So you turn the noise up and you create noise models based on studying smaller numbers of qubits and things and understanding the physics of the qubits. Then you can fit the results for certain properties, like this would be some operator you want to measure at a later time on a certain site. You fit the results you get at different amounts of noise, and then you extrapolate backwards to zero noise. And you can try different extrapolation schemes to get sort of an idea of error bars and how confident you are. And when you do, the results are greatly, greatly improved by doing this extrapolation. But one important comment, by the way, is that you can also do this on the classical methods. And that wasn't really done so much in the paper. They commented on that in the conclusion, but it did leave us scratching our heads a little bit, like, couldn't they, how much better would the classical methods be if you did that for them also? And then this paper showed some really nice results. It showed that if you run this dynamics in time, here they're showing some good pictures of, you run this dynamics forward and you measure properties at later times that you can argue are only affected by a sort of light cone region of the qubits at earlier times. And these properties are things like expected values of the Pauli Z operator or expected values of certain products of Pauli X, Y, and Z on different sites or strings of sites and things. Then at short times, there's methods you can do, these light cone methods and other methods to get exact results. So these are times of only 5 time evolution steps. But already at these times, and so here's the quantum computer results, or these blue dots with these error bars. And you can see they're agreeing well with the exact results that you can get, which are these solid curves. But already at these times, certain tensor network methods that were shown in the paper are already beginning to struggle. So you see 2 methods here, these 2 brightly colored curves, matrix product state method, and another method called ISO-TNS, which is a 2-dimensional tensor network method. They're agreeing really well in this regime of the small transverse field theta. This theta is this kind of strength of this transverse field that makes the dynamics more and more quantum in a sense. But then at larger theta, they're having a lot of trouble already, and there are big disagreements in certain observables, especially here. By the way, also these green circles are the unmitigated results. If you didn't at all try to extrapolate in the error in the noise, you would get pretty poor results like this. So doing these extrapolations in the noise from the hardware really, really improves the results, and you get very close to the exact results. So it's a great paper, actually, experimentally in a lot of ways. Then most importantly, they were able to keep pushing to longer times where there's no currently known way to get totally exact results or anything for these quantities. And there still isn't. I mean, the results we'll show are not exact. They're just very accurate. But in terms of really provably exact, numerically exact results, we don't currently have ways of getting them for these times and these depths. So at this point, the quantum computer is really, doing something very non-trivial. So it's getting these values at longer depths. I think of some of these are at depths of 20 applications, for example, of the of the dynamics. And as the tensor network method shown in the paper, at least, can't keep up. They do a good job again at small theta, but then at larger theta, they just start to systematically fail. So now to kind of give a bit of background of why this is hard or challenging, at least for these classical methods, tensor networks are very powerful, as I've been arguing, but they are still, we're still kind of learning how to use them for two-dimensional problems. 1D is going very well, but 2D is still, there's a lot of frontiers there. You can use 1D tensor networks to a certain extent by kind of just shoehorning it into 2D. You just say, I'm just going to zigzag through a 2D lattice with a 1D network. And that works actually really well up to a point, but then the costs kind of balloon exponentially with the size of this transverse direction. But so it's very accurate on small kind of rectangular systems, but for big square systems, it's not very accurate. It's also been now the case for quite a while that there are 2D tensor networks. They go by various names like TNS tensor network states or PEPs, projected entangled pair states. All they really are is like the analog of a matrix product state, but with the connectivity of a 2D lattice. So you have bonds connecting, in X and Y directions. However, the algorithms for these still can leave something to be desired. Like some of them are maybe highly controlled, but extremely expensive, and others are cheap, but not very well controlled. And so still kind of a very active area of developing these 2D tensor network algorithms. However, we were able to pull one of these 2D tensor network algorithms off and get high accuracy. And so how did we do that? And the idea is that we just followed the same kind of PEPs prescription. Here I'm showing a square lattice for simplicity, but what Joey and Matt did is they put the tensors onto the same connectivity as this so-called heavy hex lattice that the IBM experiment used as well. So that's literally the tensor network that Joey and Matt programmed. It's just following the 2D connectivity. These gray tensors are kind of a technicality. They're important, but kind of play a more technical role that I won't go into. So first of all, we start with the same tensor network state that has the same topology as the experiment. And then we have to find some way to time evolve it. Now, ideally, to time evolve it or compute expectation values of this state represented by this tensor network. So I should say, first of all, you can initialize it easily into a trivial starting state, just like in the experiment, some kind of state where all the spins are pointing in the same direction or something like that. That's easy to do. You just fill in the numbers in a very simple way. But then you want to time evolve it, and it's going to become more non-trivial, and then you want to compute expected values. And mainly what that boils down to is you want to compute the overlap of the kind of ket version of the network with the bra conjugated network. That's the main thing you need to do in terms of when you actually go to apply gates or compute expected values. So I'm going to focus on that task, and all the other tasks boil down to some small changes to that basic task. So that's the main computational workload. And here, to simplify things, let me just show a bird's eye view of it so we don't have these two layers and all the lines showing. But this is really what you're running on the computer, is trying to compute these mainly compute these. And the main thing you need to do is, let's say we're going to time evolve in a way that involves touching one or two of these tensors only at a time, because we can break the time evolution down into a bunch of gates, like on a quantum circuit. So let's say we just need to touch one of these tensors, maybe because we're going to compute an expected value on that one tensor. What we need to do is we need to contract all the rest of the network around and bring things in to just a problem involving that one tensor and this outer tensor, which I'm drawing as a big black ring. So that outer tensor is something we would love to be able to compute, and we'd call that the full environment. But it turns out computing that exactly, meaning just by doing sums and products on the computer, scales exponentially. It's like a very hard exponential. So we can't do that just literally by summing things up. We have to do some amount of approximation to do that. That's a big difference from 2D to 1D. So in this work, what Joey and Matt did is they were already working on this method. We'll actually make a very, very drastic approximation for this black ring, which is like a big tensor with 4 indices sticking in. We'll just factorize it as 4 vectors. So instead of this tensor with 4 indices, it'll just be an outer product of these 4 vectors shown as these gray circles. And these vectors in this context have a sort of a jargon name called messages. And you'll see why that name, where that name comes from in a second. So you can imagine the rest of the lattice sending these messages into this core tensor here, or pair of tensors. And that's how we could expect expected value is finally, this is a simple network that you can contract cheaply. where does this name messages come from? Well, the idea is that once we've updated, say, one of these tensors, or if we want to measure something on one of these tensors, like this one, for example, we need all these messages to be prepared. We need them to carry the information about what's going on in the rest of the system to that tensor. So let's say the messages are out of date. Let's say they're old, or we don't have them, or somehow we need to compute them. What you do is you run a certain algorithm called belief propagation to converge and compute these messages. So the idea is you say, I suspect that all the messages here, this one, and this one, if you can see my pointer, are old. And so I'm going to get rid of them. And then I'm going to propagate new messages through. So you contract these 3 other messages around each tensor with this line sticking out will give you a vector. And that's the message you compute. And then you pass that message over. And now you contract these 3 and compute a new one and pass. And so you do these message passing steps where you just kind of keep going around and around a circle, passing messages left to right, top to bottom, bottom to top, right to left. You just keep going around and around and around and around. On a more general graph, you're just basically passing them like a game of telephone, like playing neighbors. You know, neighbors call their neighbors and call their neighbors. And you just pass and pass and pass and pass. And you do this until the vectors don't change anymore, or to some small tolerance. So the point, some key points about this algorithm. If the lattice is a tree, meaning if it doesn't have any loops at all, which is not the case for this IBM lattice, but if it was, this algorithm is actually totally fully controlled, essentially numerically exact algorithm. So that's an important point. So if the dynamics on a loopy lattice, like in the IBM experiment, secretly have tree-like correlations, this algorithm could still work, even though formally it's no longer controlled. The other thing is you can always run these message passing equations on any lattice, even if it has loops. You can still do it. It's a well-known idea from the spin glass field. It's a very old idea, actually. And it's very cheap because you're just passing these small vectors around. So we can push the internal bond dimension of the tensor network very high. And at least the state we're holding could capture very complex correlations and lots of entanglement, even though when we go to compute properties, we do it in this approximate message passing way. And the message passing approximation, the belief propagation idea, is pretty analogous to doing mean field theory in a sense, in the idea that it's exact on trees. But it's likely much more accurate than more old school kind of traditional ideas of mean field theory. It's sort of able to capture more non-trivial properties. And the idea of using this on tensor networks was put forward quite recently by Sahu and Swingle last year, and then has been explored more in detail in these other 2 works that I recommend. And then most importantly, you can do dynamics on top. So you're doing this message passing, and you can do it to extract properties of a tensor network, but you can also time evolve as you go, which is really powerful. So this was a nice check that Joey did. And one of our colleagues recommended this, Mike Zalatel. He said, why don't you try some smaller systems to understand better whether this approximation is justified? And so what he did is he took a piece of this larger 2D lattice, just 1 loop or 2 loops. Remember that original lattice is this huge 2D lattice, and ran this same Ising model dynamics using this message passing approximation to how we extract properties from the network. And you can see that for short times, the x-axis got a bit erased here, but this is just going in time, more and more applications of the time evolution operator, that the tensor network method Joey was using, which are these curves that are blue, tracks these crosses, tracks the dashed line, which is the exact dynamics perfectly. Then all of a sudden at a certain time, it diverges from the exact dynamics. And that's because the correlations start to go around the loop. And once they touch around both sides of the loop, then this belief propagation approximation starts to break down. So it's actually perfect for short times, and then it can start to run into trouble for longer times. But then very intriguingly, when you do 2 loops, it actually gets much, much better. So you would think if loops make it bad, then more loops would make it worse, but somehow more loops actually makes it a lot better. And then you go to 3 loops and it's again, much, much better. So there's something still here we need to understand, but it might be some kind of interference phenomenon, or maybe some phenomenon related to how mean field theory works better when you have more neighbors, something kind of in that zone, but we don't have a great understanding yet of exactly why more loops actually makes it work better. So it's something we're kind of working to understand, but it's just something for now we're taking as the empirical fact. Then Joey had already tried this for this large 2D lattice, the one I showed, this big lattice of the experiment, this guy. So he had already tried this out in that 1 week time. And what he found was that in that verifiable regime where you can get exact results that were already in that Nature paper, the tensor network method, which are these crosses, sits right on top. And then you can check the accuracy and it's extremely high. And this algorithm is so efficient that all of these calculations individually only took a few minutes to run just on a MacBook M1 laptop. So, so already at this 5 time step regime, this tensor network algorithm is extremely efficient and you wouldn't need a quantum computer to get these results. But this is just the verifiable regime showing some different properties. But what was remarkable was even for these larger depths going up to something like 20 applications of this time evolution operator of the plot on the right, then you can run this same tensor network belief propagation dynamics and get this curve, which is this blue curve, and this dashed curve, which is an extrapolated version of it, going very, very close. It's sort of perfect with the experimental results and the other tensor network methods up to here. Then deviating from these unconverged other tensor network methods, which nobody is trusting, which are understood not to be correct. And then staying very close to the experiment on all the points, except possibly for this one. So there's sort of a question about, what's actually more accurate here, the experiment or this method. And that situation is now being clarified as of even just the last week. There's more and more papers coming out, and we're going to put out a new preprint clarifying how converged this is. And we believe our results are actually extremely accurate. So as I mentioned, there's been a lot of activity in the meantime. All of these papers have come out, some within days of ours and others just in the last week or so. And the good news is they all agree more or less with our results, some extremely closely. And we're going to publish some more detailed time step analysis and showing that we believe ours are actually extremely accurate. And that's in agreement with some of the more accurate results to have come out from the classical community as well. So all of these papers are classical calculations. And interestingly, some of them use quite different methods from ours too. Like some of them use ideas having to do with Clifford circuit, something like that. So kind of to sum this part up, apparently what happened is that although for sure simulating quantum dynamics on a 2D lattice is a very hard problem in general, apparently this particular 2D dynamics involving these large time steps and Ising model and this particular lattice happens to have tree-like correlations. So then tree approximations, this message passing approximation to contracting a tensor network works very, very well. And it's as if the loops just play very little role in the correlations of the quantum state. And then more, looking in the future, this belief propagation tensor network method, which is a very kind of radical approximation to this tensor network, is so effective for these dynamics. It's getting us to wonder, are there lots of other problems in 2D or maybe even in 3D and so on, where this could track the dynamics of quantum systems. And if it works, you can study very large quantum systems just on a laptop. So that's pretty exciting for us. So that's the end of the talk. And kind of summing up both of the talks, tensor networks are this very efficient way to work directly in very high dimensional spaces. You don't have a sign problem. You can measure all kinds of properties and you can understand entanglement. So they're ideal for simulating quantum algorithms. They're really a very natural connection to quantum computing and tasks you could envision for a quantum computer like the one I just showed. And there's an emerging boundary where I would say we're just still figuring out which tasks should go on the quantum hardware side and which tasks actually you can just do on a classical computer. And not every task that you would write as a quantum circuit automatically needs a quantum computer. Some quantum circuits, like the quantum Fourier transform, turn out to be really better understood as classical algorithms. So now we're, kind of finding that these tensor network methods for two-dimensional systems are already maturing, and there could be tons of applications of this. I mentioned the lattice gauge theory one earlier. There's lots of applications in condensed matter, of course, so that's a pretty exciting direction. So thanks for your attention, and if you have any questions, let me know.
Awesome, that was fantastic. We had some questions during, but are there further questions now? Yeah, please go ahead.
So I'm curious about the fact that the belief propagation worked when loops were involved. The fact that all loops somehow reduced. You mentioned some kind of interference. Do you suspect this is specific to this problem, or is it maybe a more general feature that you're looking at?
I'm kind of having to, it's a great question. It's really timely. I'm feeling really motivated to catch up more on the belief propagation literature, because I've been kind of pretty aware of it for a long time. And I think, to answer your question, I think it's more general. And what I was aware of, but not at all expert in, is that there's a whole community of people in classical StatMech, specifically studying glassy systems, spin glasses, and things like random classical Ising models on arbitrary graphs in 2D, but also in higher dimensions. And that field, that community, has understood now for quite a while that belief propagation can work extremely well. And they've been studying random graphs, so definitely graphs with loops, and getting excellent results. So a pretty famous result is that there's a method that's sort of one tick beyond belief propagation. It's called survey propagation, kind of like a dual belief propagation. And it can get what's called the SAT-unsat transition of the 3-SAT problem and higher kind of K-SAT, I think, very accurately on random graphs and things. So I think there is a deeper general understanding of that this method, BP it's called, can work really well in cases with loops for all kinds of reasons, actually.
Further questions? Let me actually jump in. Just so, would a problem that is just a normal 2D lattice, I mean, that seems like a problem with the most loops. So would that be something that could be very accurately described with this method?
I think in general, no. I think, there will be cases, but I think when the loops get very small, like on a square lattice, if that's what you mean, I think it can kind of fail there. And I showed that one case with a single loop, and it really fails after a certain point. But then again, that's where I think all I can really say is that you were both asking exactly the right question, but I don't myself at this time have such a great answer as to why these work so well. So again, I think now there needs to be a conversation happening more between the tensor network community and the spin glass community to see if we can translate their understanding over more into these quantum problems, because their understanding is more framed in these classical Ising model problems. And I think they do have this understanding that problems where naive BP would fail, if you do this like dualization of BP, it can succeed. They have a deep understanding of that. So I think there might be a lot of work to do now to see what are the quantum systems in 2D where that could also happen.
So another question from mine in terms of storage space reduction. Right? I'm running into many problems where we have many particle correlations, but in surprisingly low dimensional systems, this is particle physics stuff where you say produce jets, right, going out, and what you record is essentially directions. So you have a sphere of directions playing the role of your configuration space in a sense, plus one other direction has to do with the renormalization scale. But we are trying to track many particle correlations, and that, of course, when you try to do a calculation, becomes costly very quickly, right? If you have track 4 points on a sphere, and you have all possible correlation, all possible locations. Question is, can one translate this into something that, what kind of entanglement issues do you expect? Can one hope for cheaper ways of talking about this on a computer?
I think so. I'd have to understand better exactly the kind of types of mathematical objects you have, but for sure, one thing that we're doing a lot now with tensor networks, not just us, but there's a few people in our field getting into this, is working with functions of continuous variables, say in 3D, but even in 4D or 8D. So people are using tensor networks to solve things like 8-dimensional partial differential equations, like for plasma physics. That's one area where these are being used today. But in terms of if it was really like, so if it's kind of few body quantum problems, but in continuous space in say 4 dimensions or 3 dimensions, this could be a really, really good direction for tensor networks, actually. Scattering problems. So there's a way to do it for sure. And we're actually kind of trying some of those out right now. But then if it's one of these really mini body kind of second quantized type of problems, like the lattice gauge theory example, that's also very possible, but a bit stuck now to kind of slightly lower dimensions, like 2+1 at the moment. But can still be a good, I think it's still a direction that's going to grow and grow and grow. But then the particular details would have to be mapped over. But the good thing is literally any problem, I think, as you know, could be mapped to a tensor as long as you have enough indices. And then you can always try to then break that tensor down into these MPSs or these tensor network states. So I think the number of applications here is really endless, and it's just sort of, we're still the kind of early days.
Cool. I had a couple more questions. So do you suspect that this method was so effective on this hexagonal loops because the interaction was nearest neighbor versus something that was a larger distance?
Yeah, great point. I think so. I think that's for sure part of it. So definitely the fact that the method just works no matter what up to a certain time totally perfectly was for sure because of the next neighbor, because the next neighbor means that the light cone grows kind of as slowly as possible in some sense. And so as long as the light cone doesn't wrap around a loop, we're sort of rigorously guaranteed that the belief propagation will be exact. Then once it wraps around the loop, now things are more empirical, and we're into that territory of like, maybe there's interference, maybe there isn't, and these fuzzier points that I don't totally understand yet. So the nearest neighbor helped to kind of delay when we reach that time when the approximation kind of starts to bite. And then there's just more subtle things too that we understand more from experience, but we don't have a great theory for, which is that it's kind of long been known by experience in our field that Ising model is a particularly easy model in certain ways. Like somehow the Ising model dynamics always has the least entanglement. But so basically saying that if these experiments could implement something like the Heisenberg spin model or other non-Ising models, that's another thing too that would possibly make the correlations a lot more complex and kind of grow quicker. So yes, I think that was a big part of it.
Nice. And then yeah, you mentioned the word entanglement, which is actually exactly right where I was going, which is you talked about basically summing over all the outside states and then reducing yourself down to this smaller block. That then lead to some idea about entanglement entropy in the system.
It does, yeah. So interestingly, you can still kind of access the entanglement, even though it looks like these messages seem like you're completely chopping the system. Like in this drawing of it, it looks like you've just completely detached all the parts of the system. So you'd think you would have kind of removed all the entanglement, but you can still think of the messages individually as carrying parts of the entanglement, and you can look at them and you can kind of think of the entanglement as being created by like taking the product of the entanglement of this cut, that cut, that cut. So there's still actually a lot of entanglement there, but it has to be tree-like in what this BP approximation could capture. So the size of the messages, if they're big, can carry most or a lot of the entanglement. But then if the entanglement somehow had a multipartite entanglement, or there was entanglement that involved properties going around a loop, that somehow might get thrown away. So it's interesting because it starts to get away from the realm of like purely how much entanglement off into this thing of like multipartite or loop entanglement, or these things that aren't totally actually all that well understood yet, which is good. So it kind of pushes the boundary out. And one nice thing about tensor networks is that they've actually led to really great theory developments. Like for example, all quantum phases of matter in 1D can be classified purely in a tensor network language. So we may see further refinements of understanding of 2D entanglement also through this toolbox.
Very cool. I think that's everything my side. Last call for questions. Super. Well, Miles, thank you so much. This is really, really great. Thank you for taking the time, and have a great trip to Japan. Thank you so much.
Okay, thanks for all the great questions and the interest. Appreciate it.
Fun.
Bye, everybody.